Welcome to GCP Backend Services. Welcome to the channel. I would appreciate it if you would subscribe. I produce videos daily covering AWS, Azure, and GCP also. Hit the notification bell to get notified of new videos. Let me walk you through one of the most powerful aspects of Google Cloud. Building backend services that can scale from zero to millions of users without breaking a sweat. I've been working with these technologies for years, and I'm excited to share what I've learned. You know what's amazing about GCP's backend services? They give you enterprise-grade capabilities that used to require entire DevOps teams to build and maintain. We're talking about auto-scaling that responds to traffic spikes in seconds, auto-healing that replaces failed servers before your users even notice, and global load balancing that routes traffic to the closest healthy backend. Today, I'll show you exactly how to build this infrastructure using real commands you can run in your terminal. We'll start simple and build up complexity, so by the end, you'll have a complete understanding of how these pieces fit together. Trust me, once you see how this works, you'll never want to manage servers manually again. The complete architecture overview. Before we dive into commands, let me paint you the big picture. This diagram isn't just pretty boxes. These are the exact objects we're going to create, with the actual names you'll use. I always start with the architecture because understanding the flow helps everything else make sense. Picture this. When someone visits your website, their request travels through a chain. It starts with your static IP called WebLBIP, flows through forwarding rules that listen on specific ports, hits target proxies that handle the protocol details, goes through URL maps that decide which backend to use, and finally reaches your virtual machine instances. Here's the key insight that took me a while to grasp. There are two fundamentally different approaches to managing your backends. With managed instance groups, Google becomes your operations team, automatically creating virtual machines, monitoring their health, and scaling them up or down. With network endpoint groups, you're the traffic director, manually deciding which specific endpoints get traffic. The order of creation matters tremendously. You can't create a backend service without a health check, and you can't create forwarding rules without target proxies. Think of it like building a house, foundation first, then walls, then roof. Understanding load balancer types. Choosing the right load balancer is like picking the right tool for a job. Use the wrong one and you'll either overpay or underperform. Let me break this down based on real-world scenarios I've encountered. Global HTTP/HTTPS load balancers are your workhorse for web applications. They operate at layer 7, which means they're smart enough to look inside your HTTP requests and make routing decisions. Want to send API calls to one set of servers and static files to another? No problem. Need to route different domains to different backends? Easy. The global part means your users get routed to the closest available backend automatically. Now, if you're running a TCP application that doesn't speak HTTP, maybe a database proxy or a game server, that's where TCP proxy comes in. It still gives you global reach, but it works at layer 4, so it's all about connections, not HTTP headers. Regional load balancers are for when you need absolute maximum performance and you're okay with regional scope. Think high-frequency trading or real-time gaming where every millisecond counts. Internal load balancers are perfect for microservices that only talk to each other inside your VPC. Setting up your environment. Alright, before we start building anything, let's get your environment set up properly. I've seen too many people skip this step and then wonder why their commands fail later. Trust me, spending 2 minutes here saves hours of debugging. First, we're setting environment variables because typing the same project ID over and over gets old fast. The export command creates variables you can reuse. Project ID should be your actual project ID. Region is where you want your resources, and zone is a specific data center within that region. The gcloud auth login command opens your browser and lets you sign in with your Google account. For learning, this is perfect. In production, you'd use service accounts, But let's keep it simple for now. Those gcloud config set commands are telling the CLI tool your default settings. It's like setting your home address. Now you don't have to specify it every time. The services enable commands turn on the APIs you'll need. Think of APIs like services at a restaurant. You need to tell the waiter which ones you want available. Pro tip: the compute API is for virtual machines and load balancers. Logging is for seeing what's happening in your apps, and monitoring is for tracking performance metrics. MIG versus NEG decision making. This decision point is huge, and I wish someone had explained it to me this clearly when I started. The choice between MIGs and NEGs fundamentally changes how your infrastructure behaves, and there's no going back once you've built everything. Think of managed instance groups as hiring a really good operations team. You give them a template that describes how you want your servers configured, and they handle everything else. Traffic spike at 3 a.m.? They spin up more servers. One server crashes? They replace it before your monitoring even notices. You literally sleep better at night knowing Google is watching your infrastructure. Network endpoint groups are for control freaks, and I mean that in the best way. You decide exactly which endpoints get traffic, when they get added or removed, and how they're configured. Want to include a cloud run service, a virtual machine, and an external API all behind the same load balancer? NEGs let you do that. Here's my rule of thumb. If you're running virtual machines and you want them to scale automatically, use MIGs. If you need precise control over traffic distribution, or you're mixing different types of backends, use NEGs. The decision tree on the slide will walk you through the specifics, but that's the mental model that works for me. Creating your first NEG. Let's start building. I'm beginning with NEGs because they're conceptually simpler. Think of them as smart address books that tell your load balancer where to send traffic. The first command creates a zonal NEG. Here's what each part does. The name web app NEG is what you'll route reference later. The zone parameter tells Google which data center this NEG lives in. The network and subnet parameters specify which virtual network to use. Default is fine for learning, but you'd use custom networks in production. The default port saves you from specifying port 80 every time you add endpoints. Internet NEGs are fascinating. They break the traditional boundary of cloud infrastructure. The network endpoint type of Internet IP port tells Google this NEG will contain external endpoints. The global flag means you can use this NEG in global load balancers. This is perfect for hybrid setups where you're migrating workloads gradually or integrating with external services. Serverless NEGs are where things get really interesting. Instead of managing virtual machines, you're pointing directly to managed services like Cloud Run. The Cloud Run service parameter tells the NEG which Cloud Run service to route traffic to. Google handles all the complexity of connecting your load balancer to the serverless platform, managing NEG endpoints. Now comes the fun part: populating your NEGs with actual endpoints. This is where you see the granular control that NEGs provide, and why they're so powerful for complex architectures. The update command with add endpoint is how you tell the NEG about new destinations for traffic. When you specify instance equals web server 1, you're telling Google to send traffic to that specific virtual machine instance on port 80. The beauty here is precision. You can add exactly the instances you want, when you want them. Adding IP endpoints is even more flexible. Instead of referencing a virtual machine by name, you're giving the NEG a raw IP address and port. This is incredibly useful when you have legacy servers, physical machines, or services running on custom configurations that don't fit the standard virtual machine model. The remove endpoint command is just as important as adding. In production, you'll constantly be taking servers out for maintenance, decommissioning old hardware, or removing unhealthy endpoints. NEGs make this surgical. You can remove one specific endpoint without affecting any others. Notice how every command specifies the zone for zonal NEGs. That's because endpoints in a zonal NEG must be in the same zone. Global NEGs like Internet NEGs don't have this restriction. Understanding MIG architecture. Now let's talk about managed instance groups, which honestly feel like magic when you first see them work. I remember the first time I watched a MIG automatically replace a failed server. I just sat there thinking, why did I ever manage servers manually? The diagram shows the 4 superpowers that MIGs give you. Automatic scaling means your app handles Black Friday traffic spikes without you waking up at 2 a.m. to manually add servers. You set policies like when CPU hits 70%, add more instances, and Google does the math and handles the execution. Auto healing is like having a 24/7 operations team that never sleeps. When the health check detects a problem with an instance, the MIG doesn't just restart it, it completely replaces it with a fresh virtual machine built from your template. This eliminates so many classes of problems that simple restarts can't fix. Rolling updates let you deploy new code with zero downtime. You create a new instance template with your updated application, and the MIG gradually replaces old instances with new ones. You control the pace, so you can deploy safely. Regional MIGs automatically spread your instances across multiple zones. If an entire data center goes down, your app keeps running on instances in other zones. This kind of fault tolerance used to require massive engineering effort, now it's just a checkbox. Creating instance templates. Instance templates are the DNA of your virtual machines. They define exactly how every instance in your MIG gets created. Getting this right is crucial because it affects every single server you will ever run. Let me walk you through this startup script because it is doing several important things. First, it updates the package list and installs Nginx. Pretty standard stuff. But then, it creates a custom index page that shows the server hostname and zone. This is incredibly useful for testing because you can actually see which server is responding to your requests. The health check endpoint creation is critical. We are creating a simple endpoint that returns OK when the server is healthy. Your load balancer will hit this endpoint regularly to make sure the server is ready to handle traffic. Now for the instance template command itself. The machine type E2 medium gives you a balanced compute option. Not too big, not too small. The network interface parameter specifies you want premium network tier and the default subnet. The image family Debian 11 means you will always get the latest Debian 11 image, which includes security updates. The tags parameter is important for firewall rules. These tags let you apply firewall rules to all instances created from this template. The scopes parameter determines what Google Cloud APIs your virtual machines can access. Cloud platform scope is broad, but in production you would want to be more specific. Creating and configuring MIGs. Here's where the magic happens. We're creating the actual managed instance group that will spawn and manage our virtual machines. I always recommend regional MIGs over zonal ones, unless you have very specific requirements. Let's break down this command. The name web server MIG is what you'll reference everywhere else. The base instance name parameter determines how individual virtual machines get named. With web server as the base, you'll get instances named like web server ABC 123, web server def 456, etc. The random suffixes prevent naming conflicts. The template parameter points to the instance template we just created. The size parameter tells Google to create 3 instances initially. The region parameter makes this a regional MIG, which means Google will automatically distribute these 3 instances across different zones for high availability. That target distribution shape parameter is interesting. Balanced means Google will try to keep an equal number of instances in each zone. If one zone has problems, the instances will redistribute to healthy zones. The named ports command is absolutely critical for load balancing. You're telling the load balancer, when I say HTTP, I mean port 80, and when I say HTTPS, I mean port 443. This abstraction lets you change ports later without reconfiguring your entire load balancer. Auto-scaling configuration. This is where MIGs become truly intelligent. Auto-scaling transforms your infrastructure from static servers to a dynamic system that responds to actual demand. Let me explain how this works in practice. The set autoscaling command creates policies that Google monitors continuously. The max num replicas of 10 means you'll never have more than 10 instances, which protects you from runaway scaling costs. The min num replicas of 2 ensures you always have at least 2 instances running for redundancy. Target CPU utilization of 0.7 means when the average CPU across all instances hits 70%, start adding more instances. This is usually a good sweet spot, high enough to use your resources efficiently, but low enough to handle sudden spikes. The cool-down period is crucial for preventing oscillation. It forces the system to wait 90 seconds between scaling decisions, so you don't get into a situation where instances are constantly being added and removed. Those scale and control parameters are really important for user experience. Max scaled in replicas of 2 means you'll never remove more than 2 instances at once when scaling down. The time window of 120 seconds means the system looks at a 2-minute average before deciding to scale down. This prevents aggressive scale downs that could hurt performance. Health checks, your application's guardian. Health checks are the unsung heroes of reliable infrastructure. They are constantly monitoring your applications and making split-second decisions about which servers are ready to handle traffic. I have seen health checks save companies from outages more times than I can count. Let us walk through this HTTP health check command. The create HTTP part tells Google you want to monitor HTTP endpoints. The port 80 parameter specifies which port to check. This should match where your application actually listens. The request path/health is the URL path the health check will hit on each server. The timing parameters are critical to get right. Check interval of 30 seconds means Google will test each server every 30 seconds. Timeout of 10 seconds gives each check 10 seconds to respond before being considered failed. Unhealthy threshold of 3 means a server needs to fail 3 consecutive checks before being marked unhealthy. Healthy threshold of 2 means it needs to pass 2 consecutive checks to be considered healthy again. Here is a pro tip from painful experience. Make your health check endpoint actually verify that your application is working. Do not just return OK. Check your database connection. Verify critical services are responding, and make sure you can actually serve user requests. A health check that passes when your app is broken is worse than no health check at all. Configuring auto-healing. Auto-healing is where health checks and MIGs work together to create self-repairing infrastructure. This is honestly one of my favorite features because it means I sleep better at night knowing my systems can fix themselves. The set auto-healing command connects your health check to your MIG when you specify the health check parameter. You're telling the MIG use this health check to determine if instances are healthy. The initial delay parameter is absolutely critical. It gives new instances 300 seconds, or 5 minutes, to fully start up and become ready before health checks begin. Here's what happens in practice. Let's say one of your servers starts having problems and fails 3 consecutive health checks. The MIG doesn't just restart the instance. It completely destroys it and creates a brand new instance from your template. This eliminates entire classes of problems that simple restarts can't fix, like corrupted file systems, memory leaks that persist across restarts, or configuration drift. The beauty of auto-healing is that it is proactive. By the time your monitoring alerts you that something went wrong, the system has already fixed it and is serving traffic normally again. Your users might never even notice there was a problem. One thing to watch out for. If your initial delay is too short, healthy instances might get replaced because they haven't finished starting up when health checks begin. If it is too long, actually broken instances will serve bad traffic for too long. Backend services. Traffic distribution engine. Backend services are where all the pieces start coming together. Think of them as traffic directors that know about your servers, monitor their health, and make intelligent decisions about where to send each request. Let's break down this backend service creation command. The create backend services part is straightforward, but the parameters are doing a lot of work. The protocol HTTP parameter tells the backend service to expect HTTP traffic and handle it appropriately. The port name HTTP parameter references the named port we defined in our MIG. Remember when we said HTTP means port 80? This is where that mapping gets used. The health checks parameter connects this backend service to our health check. Now the backend service knows how to determine if backends are healthy and ready to receive traffic. The global flag means this backend service can be used by global load balancers. Enable logging is incredibly valuable for troubleshooting and optimization. The logging sample rate of 1.0 means log every single request. In production with high traffic, you might set this to 0.1 to log 10% of requests to save on logging costs while still getting good visibility. The protocol setting is crucial. It must match how your application actually serves traffic. If your app only accepts HTTPS, use HTTPS protocol. If it serves plain HTTP, use HTTP protocol. Mismatching this will cause connection failures. Adding backends to services. This is where you connect your MIGs or NEGs to your backend service. The balancing mode determines how traffic gets distributed. Utilization mode is perfect for MIGs with auto-scaling. It distributes traffic based on how busy each backend is, and when utilization hits your target, like 80%, auto-scaling kicks in to add more instances. Rate mode gives you precise control over how many requests per second each backend handles. This is useful when you know the capacity of your instances. The capacity scaler is a multiplier that lets you temporarily reduce or increase a backend's capacity without changing the balancing mode settings. It's great for gradual rollouts or maintenance. Load balancing modes explained. Understanding balancing modes is crucial for getting the performance and scaling behavior you want. Each mode optimizes for different scenarios. Utilization mode works best with auto-scaling MIGs because it automatically triggers scaling when backends get busy. It's the most hands-off approach. Rate mode gives you precise control and is perfect when you know exactly how many requests your instances can handle. It's more predictable but requires more tuning. Connection mode is specialized for TCP/SSL proxy load balancing where you care about concurrent connections rather than requests per second. The key parameters let you fine-tune the behavior. Max utilization of 0.8 means don't send more traffic to a backend if it's already 80% busy. URL maps, the traffic director. URL maps are the brains of your load balancer. They examine incoming requests and decide which backend service should handle them. This is where you can get really creative with traffic routing and build sophisticated architectures. The basic create URL maps command creates a simple map that sends all traffic to one backend service. The default service parameter specifies where traffic goes when no specific rules match. This is your fallback. Always specify a reliable backend here. But the real magic happens with path-based routing. The add path matcher command lets you create sophisticated routing rules. The path matcher name is just a label for this set of rules. The path rules parameter is where it gets interesting. You're saying, if the URL starts with /API/, send it to the API backend service. If it starts with /static/, send it to the static backend service. Host-based routing takes this further. The add host rule command lets you route based on the domain name in the request. So api.example.com traffic can go to different backends than www.example.com traffic, even if they're hitting the same URL path. This enables microservices architectures where different teams can own different parts of your application. A /B testing where you route a percentage of traffic to new versions, and content-based routing where images go to CDNs and API calls go to application servers. SSL certificates and HTTPS setup. HTTPS isn't optional anymore. It's a requirement for any serious web application. Fortunately, Google makes SSL certificate management much easier than the traditional approach of buying certificates, tracking expiration dates, and manually renewing them. The Create SSL Certificates command with Google Managed Certificates is fantastic for most use cases. You just specify the domain's parameter with all the domains you want covered, and Google handles everything else. The global flag makes this certificate available to global load balancers. Here's what happens behind the scenes. Google automatically provisions certificates from Let's Encrypt or their own CA, handles all the domain validation, and even automatically renews them before they expire. You literally never have to think about certificate management again. There's one important caveat. Google can only issue certificates for domains that already point to your load balancer IP, so you need to set up DNS first, then create the certificate. The provisioning process can take several minutes, and your HTTPS won't work until it's complete. Self-managed certificates give you more control when you need it. Maybe you already have certificates from your corporate CA, or you need wildcard certificates that cover unlimited subdomains. The certificate and private key parameters let you upload your own certificates that you manage yourself. Target proxies, the protocol handlers. Target proxies handle the specific protocols. They connect your forwarding rules to your URL maps. Think of them as protocol-specific adapters. HTTP proxies handle unencrypted traffic on port 80. HTTPS proxies handle encrypted traffic on port 443 and need SSL certificates attached. You can attach multiple SSL certificates to a single HTTPS proxy. This is useful when you serve multiple domains from the same load balancer. The QUIC override enables HTTP/3 support. This can improve performance for supported clients. TCP and SSL proxies are for non-HTTP traffic. They provide global load balancing for TCP-based applications. Forwarding rules and IP management. Forwarding rules are the front door to your load balancer. They define which IP addresses and ports accept traffic and where that traffic gets directed. Think of them as the receptionists who greet visitors and send them to the right department. First, we reserve a static IP address with the G-Cloud Create Addresses command. The global flag makes this IP available worldwide. An IP version IPv4 gives you a standard IPv4 address. Why reserve it separately? Because you want a stable IP that does not change when you modify your load balancer configuration. Your DNS records will point to this IP. The G-Cloud Create Forwarding Rules commands are where traffic actually enters your system. The address parameter ties the forwarding rule to our reserved IP. The global flag matches our global backend service. The target HTTP proxy parameter tells the forwarding rule where to send traffic, in this case, to our HTTP proxy. The ports 80 parameter means this rule only accepts traffic on port 80. Having separate forwarding rules for HTTP and HTTPS is important. The HTTP rule on port 80 usually redirects to HTTPS, while the HTTPS rule on port 443 handles your actual traffic. Both rules use the same IP address but different ports. Pro tip: reserve your IP addresses in production as soon as possible. If you do not reserve them, Google might reassign them when you recreate your load balancer, breaking all your DNS records. Understanding the complete traffic flow. Let me walk you through what happens when someone visits your website, because understanding this flow helps everything else make sense, and makes troubleshooting much easier when things go wrong. It starts with a user typing your domain into their browser. DNS resolution happens first. Their computer looks up your domain and gets back the static IP address we reserved. The request then hits Google's global load balancing infrastructure, which is present in data centers worldwide. The forwarding rule examines the incoming request and says this is HTTPS traffic on port 443, so I'll send it to the HTTPS target proxy. The target proxy handles SSL termination. It decrypts the traffic using your SSL certificate, so your backend servers don't have to deal with encryption overhead. Next, the URL map examines the decrypted request. It looks at the host header, the URL path, and potentially other attributes to decide which backend service should handle this request. This is where path-based routing happens. API calls might go to one backend service while static file requests go to another. The backend service then performs the actual load balancing. It checks which backends are healthy using the health check results, applies the balancing algorithm you configured, and selects a specific virtual machine instance to handle the request. Finally, the request reaches your application server. The response travels back through the same chain in reverse, getting logged and monitored at each step. Complete implementation guide. Now let's put it all together with a complete implementation. This step-by-step process shows you exactly how to build a production-ready backend service from scratch. We start with the instance template because everything else depends on it. The template defines how your virtual machines will be configured, including the startup script that installs and configures your application. Next, we create the MIG using that template. This immediately starts creating virtual machine instances based on your template. Then we configure autoscaling so the MIG can respond to load changes. The health check comes next. This is what monitors your application's health and enables auto-healing. The backend service ties everything together and defines how traffic gets distributed. Finally, we build the load balancing chain. URL map for routing, target proxy for protocol handling, and forwarding rules to accept traffic on specific IPs and ports. Monitoring and best practices. Your backend service is running, but the real work is just beginning. Monitoring and optimization are ongoing processes that separate hobbyist projects from production-grade systems. Let me share what I've learned about keeping these systems healthy. The described commands shown here are your diagnostic tools. When something goes wrong, and it will, these commands show you the current state of your resources. The backend services describe command shows you which backends are healthy, what their utilization looks like, and any error conditions. This is often the first place I look when debugging issues. Load balancer logs are pure gold for understanding your application's behavior. They show you response times, error rates, which backends are serving traffic, and geographic distribution of your users. Set up dashboards for key metrics like average response time, error rate, and requests per second. Health check monitoring deserves special attention. If your health checks are failing intermittently, you might have a flaky application or network issues. If they're failing consistently, you have a real problem that needs immediate attention. Auto-scaling metrics tell you if your scaling policies are working correctly. Are you scaling up fast enough during traffic spikes? Are you scaling down too aggressively and hurting performance? The monitoring data tells the story. Regular testing is crucial. Manually trigger auto-scaling events, simulate server failures, and verify that your auto-healing works as expected. Better to find problems during controlled tests than during real outages. Conclusion and next steps. We've covered a lot of ground today, and I hope you're feeling excited about what you can build with these tools. When I first learned about GCP's backend services, I was amazed at how much enterprise-grade functionality was available through relatively simple commands. Think about what we've accomplished. We built auto-scaling infrastructure that responds to demand in real-time, auto-healing systems that replace failed servers automatically, global load balancing that routes traffic to the closest healthy backend, and SSL termination that handles certificate management for us. This kind of infrastructure used to require teams of specialists and months of custom development. The key insight is that Google has abstracted away the complexity while still giving you control over the behavior. You don't need to understand the internals of load balancing algorithms or health check distribution. You just need to understand what business outcomes you want and configure the parameters accordingly. My advice for next steps: start with a simple HTTP load balancer in a test environment. Get comfortable with the basic concepts before adding complexity like HTTPS, multiple backend services, or advanced routing rules. Build your confidence with small experiments before moving production workloads. Remember, the goal isn't to use every feature, it's to use the right features for your specific needs. Start simple, monitor everything, and gradually add sophistication as your requirements evolve. Thank you for your attendance.